practicing more geometric proofs. So this one's a guided proof, and then the rest we're going to write on our own. So we are given that AC is equal to BD. So that's this is equal to this here. And we want to prove that AB and CD are equal, which makes sense because BC is the overlap between AC and BD. So BC is going to be congruent to itself, but we need to break this up into simple steps. So your first step is your given, always. All right. Now, to get all of this red segment, AC, it consists of parts, two parts, AB and BC. So using the segment addition postulate, I can say the whole segment AC is equal to AB plus BC. Same with the blue segment here. I can say that segment BD is equal to BC plus CD. That is the segment addition postulate, and remember this is how I abbreviated it in the past. But now what we can do if we look at these two equations and what we were given in step 1, we know that in step 1 we have AC equal to BD. So what I could do is I can take AC and I can substitute it in to BD to get AC is equal to BC plus CD. And notice my first statement in steps 2 and 3 are exactly the same. I just rewrote it. That's one way of looking at it. Another way of looking at it is since BD is both equal to AC and BC plus CD, that means I can set it equal to each other using the transitive property of equality. So either would work. It's up to you which one you want to use more. It's up to you. Now, looking at step 3 and step 4, there's two ways of looking at this. In step 3, since both AC is equal to both of these things, I can set both of those things equal to each other using the transitive property of equality. Or another way of looking at it is since AC is equal to AB plus BC and also BC plus CD, I can take the AB plus BC and substitute it in for AC in the bottom statement to get the statement here. So again, this is either substitution or transitive property of equality. That's up to you. This is how we could abbreviate substitution, and this is how we can abbreviate transitive property of equality. And then lastly, looking at steps 4 to step 5, I should notice that both sides of this equation have a BC. So if I use subtraction, I could subtract BC from both sides, and I'd be left with AB is equal to CD, which is exactly what I was trying to prove in the first place. That is just the subtraction property. And that's it. All right, number 2, we're writing this one ourselves. I have that RS is 8 units long, and RT, which is the whole thing, is 34 units long. So I want to prove that ST is 26, which makes sense, because if I have RT, which is 34, I could just subtract 8 from it to get ST is 26. But we need to break it down into more simple steps using the properties that we have been given, or that we have learned. So first statement is given, okay? Our next statement, we cannot substitute things into properties until we say our property. And our property states, that the segment addition postulate states, that if I have RS plus ST, that equals my whole segment, RS, there is no way that we should already manipulate this, because that's not what the segment addition postulate states. The segment addition postulate states exactly what I wrote in part 2. And notice I don't have segment bars on top of each of these segments because I'm dealing with an equation. If I was dealing with congruent statements, they would have segment bars. All right, next I can use substitution to take this 8 and put it in for RS, and to take this 34 and put it in for RT. Now I can only use substitution because I'm not stating that something equals something and it equals something else, so they're equal to each other. That would be transitive property. This, I'm actually taking numbers and I'm putting them into an equation. That is only substitution. And then what I can do is I can subtract 8 from both sides to get ST is equal to 26. And this is a way you can abbreviate subtraction property. All right, looking at number 3, I have angle GBW is a right angle, and I have the measure of angle GBT, which is 35 degrees, and I'm going to try to prove that the measure of angle TBW is equal to 55 degrees, which again makes sense because this whole angle is going to be 90 degrees, but we do need to state that in our proof, knowing that it's a right angle. So let's first go ahead and state that we have angle GBW is a right angle. This is how you can abbreviate right angle. And I'm going to state my other part of my given as well. Now, the definition of a right angle gives us that the measure of angle GBW then is 90 degrees. That's important. Now we're going to use the angle addition postulate, which is the only way that you can write it. You cannot manipulate this postulate in any way. So I have the measure of angle TBW plus the measure of angle GBT is equal to the measure of angle GBW. Notice I'm doing the measure of the angles because I'm dealing with equal signs. That's the angle addition postulate, which I have abbreviated here. Then this is just like the one before it. I can now take this 35 and substitute it in here. And I can take this 90 degrees and substitute it in here. This is only substitution. This is not transitive property at all. And then, using subtraction, I can subtract 35 from both sides to get the measure of angle TBW is 55 degrees, which is exactly what we were trying to prove. Moving on to the next page. AD bisects angle ABC, or sorry, BAC, sorry. So BAC is this angle right here. And if AD bisects that angle, that means that angle 1 and angle 2 will be congruent, but we will need to write that in our proof. We also are given that angle 1 and angle 3 are congruent. So it would make sense that angle 2 and angle 3 would be congruent, because angle 1 is congruent to both angle 2 and angle 3. That's our plan. So step 1 is our given, always. And then we're going to use the definition of an angle bisector to say angle 1 and angle 2 are congruent. Now, since angle 1 is congruent to both angle 2 and angle 3, I can say that they're congruent to each other. I cannot use substitution on this one because I'm dealing with congruent symbols. I can only use the transitive property of congruency for this. All right, looking at number 5, we're going to write down our given, and let's mark our figure. So I have CD congruent to EF and FG. So it makes sense that EF and FG would be congruent. We're going to need to write that. And then if EF and FG are congruent, then that means that F would be the midpoint, because the midpoint cuts a segment into 2 congruent pieces. So let's write this down. Since CD is both congruent to EF and FG, we can say EF and FG are congruent to each other. This is only the transitive property of congruency. It is not substitution. We cannot use substitution with congruent symbols. And then if I know that EF and FG are congruent, then that means F is the midpoint of this segment, because that's just the definition of a midpoint. All right, we are on our last and most challenging proof of this background information lesson. So we want to prove that KH and UF are congruent, knowing that KU is equal to HF. It makes sense then that KH would be equal to UF because we have both of those, that blue and red segment overlapping at HU. But then we're going to want to state that they're congruent after we state that they're equal. So our first statement is our given. KU is equal to HF. And this is pretty similar to a couple of problems ago when we used segment addition postulate. We're going to do that again. So to get KU, that is KH plus HU. But in the same statement, to get HF, that is UF plus HU. That's the segment addition postulate. Now looking at statement 1 to statement 2, if I know that KU is equal to HF, I can take KU and I can substitute it into HF in this bottom statement here. That would be looking at it from the perspective of substitution. Or you can look at it from the perspective of the transitive property. Since both HF are equal to KU and UF plus HU, we can set those things equal to each other. That would be transitive property of equality. It's up to you which reasoning you want to go with. But I'm going to rewrite this top segment. And then, actually I didn't rewrite the top segment, but I just did the substitution or transitive property in here. So now if I look at these two statements that I'm boxing in green, there's a couple of different ways we can go about it. Since KU is equal to both of these things, I can set both of those things equal to each other using the transitive property. Or, thinking about it from the perspective of substitution, I can substitute KH plus HU into KU since it's equal to KU. Up to you which statement or which justification you want to go with. Looking at this statement here, both of them have an HU. So if I subtract HU from both sides, I'm left with KH is equal to UF. Now, I'm trying to prove KH congruent to UF. So I don't want them equal to each other. I want them congruent. So I can use the definition of congruency now to state that KH is congruent to UF. All right, that brings us to the end of our background information. So we have enough practice now with proofs to go ahead and move on to our standard.